Hello everyone, today I'll talk about the optical properties of materials. So before going into detail about the optical properties of semiconductors, metals or insulators, I'll talk about something about the interaction of light with bulk materials. And these are the following phenomena like absorption, reflection and transmission will occur when light interact with the materials. So by studying the spectra of these materials, we get the huge information about the electronic energy band gaps or vibrational properties and defect inside the materials. So we get huge amount of useful information by studying these spectra. So when the light interact with the bulk materials, we got reflection in which we have a specular or diffuse reflection. Specular reflection is those in which when the incident light is equal to the reflected light, and which usually occur on the shiny surfaces like mirror or water, in which so that's why we get our images. And then the diffuse reflection occur when mostly on the rough surfaces in which the reflected light got diffused and we cannot get any images out of that. Then we have a refraction in which we got the phenomenon of total internal reflection, then dispersion or transmission of light. So this slide shows that when light interact with water, so how first if we talk about the refraction of light, then when light get absorbed into water, then refraction occurs, and the bending of light will depend on the uh, um, uh, refractive index of the medium. So if the refractive index of the material is high, then of course the light will slow down and it bends toward the normal. And this Snell's law show the refraction of light, where the ratio of n1 and n2 is equal to sine of theta 2 divided by sine of theta 1. And this shows the refraction of light, and this is also show that when light comes from rare to denser medium, it bends towards the normal, because sine of n1 sine of theta 1 is equal to n2 sine of theta 2. So in order to because this quantity is higher here, so in order to keep this equation equal, if this equation this quantity is higher, this quantity should be lower down in order to keep this equation equal. So then we have another phenomena, which is reflection here, and then light got also dispersed into different colors. So how the light interact with now solids. So light also if light interact with solid, it get transmitted, it get absorbed, or it get reflected, and that's why we get transparent, translucent or opaque objects. So now I'll give a quick review of light and photon and the history about and theories about light and photons. First, Huygens theory, which proposed that light travel in waves and through a substance like ether, and that's why he calculated with that foundation he calculated the laws of reflection and refraction. But Newton disproves Huygens theory that light was made of waves, and he argued that the geometric nature of reflection and refraction could only be explained if light were made of particles, because light waves do not tend to travel in straight lines. So by Thomas and Young's double slit experiment, which also shows the diffraction and interference of light, and which shows the wave nature of light, and that was also supported theoretically by the prediction of electromagnetic radiation by Maxwell equations. But after that, the photoelectric effect, this was also proved by the Einstein, that light has a particle nature as well. When also on the other hand, the particle properties of electron was also documented by de Broglie's hypothesis. So by end of 19th century, most physicists were confident the world was well understood that, and besides some nagging questions, but one of the question was which concern most about the spectrum of radiation which is emitted by the black body, and which was a big question. So and so there will is a black body radiation and ultraviolet catastrophe at that time. And before going into detail about the black body radiation and ultraviolet catastrophe, you first know the what is the electromagnetic light is as a electromagnetic radiation, and also the Boltzmann constant. So first I will this is light as electromagnetic wave, and the light as an electromagnetic wave is characterized by the combination of electric and magnetic field, where magnetic field is very less than the electric field. And this is how the light as an electromagnetic wave propagate from shorter wavelength to longer wavelength. Of course, if the wavelength increases in this side, then the frequency will decrease in this side. So if this is increasing, then f will decrease, and also the energy will also decrease in this side. So there will be an inverse relation of lambda and f. So so increasing energy is that side, and increasing wavelength is in this side. From shorter to wavelength longer wavelength, energy will decrease. So and the visible light is in the range of 1.62 electron volt to 3.17 electron volt. So first if I talk about the speed of light, speed of light is not a constant as it moves from one medium to another medium. When light enters, as also I told in this slide, that when light enters from denser medium, it slows down. But speed of light is in vacuum, it's a constant quantity, which is 3 into 10 to the power 8 meter per second. And for air, because the refractive index is the same, it's almost 1. So speed of light in air is almost like in the vacuum. For ice, it's 1.31, so it will be slowed down if it moved to inside the ice, or in the diamond is 2.47, because the speed of light in medium is defined by C by N. So that's why diamond get its brilliance, because of refraction and dispersion phenomena inside the diamond. So this is the light is an electromagnetic radiation, which is composed of shorter to longer wavelengths. So now the Boltzmann constant, we know that, for example, that this container in which we have gas molecules, or in which we have gas, and which is at pressure, temperature, and some pressure, temperature, and volume. So we have this equation PV by T is equal to constant. So we know that if we draw the graph PV to T, we will get a straight line. But if we moved or if we extend this line to lower temperature, there is a temperature come when at minus 273 degrees centigrade, when PV or pressure volume term will be 0. So it means that PV divided by T is not an absolute term, but it depends on the number of the molecules inside the container, and then there is a constant absolute term, which is known as the Boltzmann constant. The thing here is that PV is equal to NKT, and the thing here is that because the Boltzmann's constant is an energy term, because it's 1.4 into 10 to the minus 23 joule per Kelvin. Look like it's an energy term. So we can say that PV is also an energy term, and NKT, because PV is equal to NKT, it's also an energy term. It means that, for example, we get PV is equal to P is force per unit area, then V, and then L square into L cube, then we get F into L, which is work done. So PV can be equal to W, and work is expressed in joules. So we can say that PV is a energy terms. So if we draw the graph, so we can say that the energy of the atoms, maximum energy of the atom inside the gas is kT. It's a maximum amount of energy of the of each atom, which is kT. So if we draw a probability curve which shows that every atom has a maximum energy which is kT, and which cannot more or less than this energy, but this is a distribution of energy, and there is a maximum energy which is for every atom which is equal to kT. There is a distribution of energy, and then we have a maximum energy, like probability, maximum probability that energy of the atom is k. So now I will talk about the black body radiation and ultraviolet catastrophe. So a black body is a body which absorb all the radiation fall upon it. For example, we have a black body in a room, and it absorb all the radiation it absorb all of the radiation inside the room. So there is a time come when the body become hotter and hotter, and the room become colder and colder. But this will violate the second law of thermodynamics, which shows that the heat travel from hot body to cold body. So it means that in order to come into the thermal equilibrium, the black body, if it's a perfect absorber, then it should be a perfect emitter. So perfect black body is a perfect absorber, and then perfect emitter. And of course this kind of black body doesn't exist which perfectly absorb and perfectly emit every kind of radiations. Some of the examples of the black body include the sun and other stars, light bulb filament, and the element in toaster electric heater. So I will talk about now the what is the ultraviolet catastrophe. So this curve shows the spectra of electromagnetic radiation emitted by the hot objects. So so this also we observe in every day when we put on the fire, and first it was just warm, and then because it's just in the ultraviolet region, and then it become hotter and change the color from red to yellow and orange. So for example, we have this is the region which is visible light region, visible, and this is the infrared, and this is the ultraviolet region. So we can see that at the ultraviolet region this curves goes down. So this is known as the ultraviolet catastrophe. So here we know that as the frequency increases in this way, because the wavelength is increasing in this way, so according to the classical theory, with the increase of frequency the intensity increases, but this clearly make no sense from the perspective in energy conservation. So then this curve up to that point make very much sense. Now we can understand that as with the increase of frequency, the intensity increases up to that point, but why it falls after that? So thanks God it do that behavior, because if we sit in front of heat, we might get frazzled, or we might get burned by ultraviolet radiation if this phenomenon doesn't happen or doesn't occur. So this is known as the ultraviolet catastrophe, and that's where the Planck and Einstein postulated that the energy has to be in the packets which they called photons, and their argument was photon cannot have much energy than available. So how much energy electron available, and which we explained in the previous slide, that E is equal to maximum energy obtained or by electron is only E is equal to kT, and which is the distribution of energy, and maximum energy is the E is equal to kT, and this is this energy when we get only E is equal to kT energy electron get and come into the higher energy level, and it emit that E is equal to kT energy, just E is equal to kT energy when it falls down to lower energy level. So that's why we can say that there is a probability of maximum probability of electron to more electrons come into that region than into the ultraviolet region, because the maximum transitions occur by the inside the atom come into that region. So that's why after that region the intensity falls down, or that maybe the maximum energy comes into the that region. And thank god it happens, because other way we got burned by the high intensity like ultraviolet x-ray radiations. So this is known as the ultraviolet catastrophe. Then electric effect was the direct evidence that tell us that light comes in a discrete packet of energy called the photons, with the energy is equal to hf. So if we just consider light regarded as wave, then it could emit photoelectron at any frequency, but actually it doesn't happen. So for example, we have a setup like this in which we have two metal electrodes, and ultraviolet and x-ray will fall on one of the metal electrode, and as a result the photoelectrons will be emitted. So because of this the current will flow inside this setup will be which will be shown by this ammeter. So if we want to know the kinetic energy of the photoelectrons, we connect a battery with this setup, and as the potential will increase, or as the potential will set up across this conductor, the for example this is negative terminal, positive terminal, then the potential here will stop the further electron to come at this at this electrode. So this time the potential will be known as the stopping potential. So for example we have V is equal to E divided by Q, then V is equal to E, where E is the kinetic energy of the electrons and E is the charge of electrons. So Vs is equal to Ek, K the kinetic energy of the electron divided by E, and kinetic energy of the electron will be shown by the stopping potential into the charge of electron. So so it means that if you plot the graph energy versus frequency graph, at first there will be we see that from this graph there will be no photoelectrons emitted, but at certain frequency electron will start to emit, and this frequency is known as the threshold frequency. So if we extend the graph in the backward direction, we come to a point in which is known as the work function, and this is what the energy needed to the electron to liberate from the certain metals. So for example we have a y is equal to mx plus c, which is equation of a straight line, and here y is equal to the energy of the electron, and c is we know that the intercept on the y, so here c is equal to minus phi, and x is frequency, and mx is hf. So E is equal to hf minus phi, which we which show the energy of the electrons. So energy is hf energy, hf is the energy which we given, and minus phi is the energy which is needed to liberate the electron. So photoelectric effect show that no matter what the intensity of incident monochromatic radiation, the stopping potential was always be the same, and the kinetic energy which the electron acquire on being ejection from the surface has a maximum value which is independent on the intensity of the radiations. It means that the kinetic energy of the electron is independent of the intensity of the is independent to the intensity of the radiation. It means that just one electron can get just one photon, not more than that. So it means that electron come into the so it means that there is a quanta of energy. So the kinetic energy of so photoelectric effect tells that the kinetic energy maximum kinetic energy is independent of the intensity of the radiation. So now we have discussed how the light interact with the mediums, different medium, and then the classical and quantum theory of the about light, and we discussed the behavior of light, and now we discuss the visual appearance of and mostly I will discuss about the semiconductor and their band gaps. Material now we know that material appearance and color depend on the how light interact with the material and with the electronic configuration of the material. So high resistivity material, which are insulators, are transparent. And why? It's because they are band gaps, because they have high band gaps. Then we have a high conductivity which material, which are metals. They have metallic luster and they have no band gaps, so they absorb most light. So semiconductors are important, which can be opaque or transparent. So we will discuss the semiconductor energy band gap diagrams, which explain the appearance of material in terms of both luster and color. So the question is why silicon is black and shiny too. So for we know that the visible range is in band gap range is in 1.8 to 3.1 electron volts. So for silicon, its band gap is 1.2 electron volt. So it means that uh, for silicon, the visible band gap is larger than the energy band gap. Visible, again, this is it's a larger band than the energy band gap. So it means that E visible is larger than E gap for silicon. So this E visible is larger than the band gap of silicon. So it means that silicon absorbs all the light fall upon it, so it appears black. So why silicon is shiny? So to answer this question, we will see the next slides also, but the answer is that because there is a significant number of electrons in the conduction band, and also which these electrons are delocalized and they scatter photons. So because they scatter photons, so they look shiny. So now why glasses are transparent? Because glass is a insulator and it's a very large band gap, which is 5 electron volt. So it will not interact with the visible light. So the visible light, or all colored photons, are transmitted from the this insulator or this glass. So that's why, and there is no absorption, so that's why the material look transparent. So in the last video, I have discussed about the P and N type of semiconductors, and P and N type of semiconductors, and I'll discuss how their energy band gap look like. So it means that, for example, if we have an electron, if it's just behave like a particle, so it's have momentum associated with it, which is like this, P is equal to mv. But for electron which is bound in a crystal, it does not behave like a particle, it also behave like a wave. And moving electron in a crystal behave like a wave, and it's have a wave number associated with it, which is this. So so when in the semiconductor, in the semiconductor, when we apply the voltage, these electrons will move will move in the direction of the voltage. So for example, if we have a direct band gap in direct energy band gap diagrams, in which we have a E of valence conduction band, or E of valence band. So in these direct band diagrams, we have this y-axis term shows the energy, and x-axis shows the position of the electrons. But here in the when electrons are moving in a crystal, or when electrons are bound, we have to include its wave function and its wave number, and which is related with its wave function psi. So so it means that for a free electron, and this the solution of this bound electron will be solved by the Schrodinger equation. For example, we have a EK diagram for free electrons. Then if we want to find a solution for, so probably our simplest solution will be like this, that for free electrons, of course, because there is no potential across it, and it's there is no charged particle around it, it's a free, so its potential will be 0. So the solution can be like this, where E is directly related to energy of the electron. So we'll take the square, and in both sides, on the both sides we get E square. E is directly related to the K square. So we have a EK diagram, which by solving this equation we get a parabola of this diagram. So for bound electrons, with the boundary conditions, we have a probably a solution, sinusoidal solution with the integral multiple of n. So in a with the boundary conditions, the solution are the restricted solution, or where we have some certain solutions. So but for a free electron, their E and K diagram will be anything, or there will be any solution for that, so because they have no boundary conditions. So if we discuss now about the crystal lattice, for example, and anisotropic crystal are those mm, which properties changes with direction. It means that in a typical lattice, the distance between atom is different depending on the direction. So it means that, for example, if we want to move from this side to this side, 100, which is 100 side, its distance is simply its distance between A, which is distance between these two crystal, and crystal, which is crystal lattice. But if we move diagonally around FCC, its distance will be under root 2A, which is different. So electron may have, because of the distance is different, so electron may have different energy states depending on the which direction electron is moving, in this direction or in upper diagonal here. So so the energy states depend on the direction in which the electron is moving. So and the spacing determine the Schrodinger wave equation, wave function. So for example, we have an EK diagram of silicon and gallium arsenide. So for example, we have a if we just discuss this side of diagram, and where electrons on the top of electrons on the top of the valence band here are have a momentum k is equal to 0, because the valence band describes the electrons are covalently bonded with the lattice. So it means that they are not moving. So here the energy in k is equal to 0. And but if electron wants to move in this direction, there its energy in k will increase, probably in negative direction. So if the electron want to move from 0 to 100 direction, its energy and momentum will increase. So in the minima of the because this is the minima of the conduction band, because now we will discuss these energy states and this energy states. So the minima, because in this is the minimum level of the conduction band, upper all of the levels are empty probably, and because we discuss this as the whole holes. If it's a semiconductor, we describe these are the holes and these are the electrons. So the minima of the electron, if electron are want to move to its minima to the valence band, so electron just not change its energy, it needs to change in the momentum, because it's will change its energy in this way, and then it needs to move in this direction, in the k direction. So and this kind of the band gap is known as the indirect band gap, in which electron has to move change not its energy, also it's change its momenta. So here in the silicon, the minima is at 100 direction, and the valence band is at k is equal to 0, which shows that electron is not moving, it's bound to the lattice. So for gallium arsenide, we have the maxima of the valence band is direct below the minima of the conduction band. So if electron want to make its transitions from conduction to valence band, it just need to change its energy, not need to change its momentum k. So yeah, so it's mean that direct band gap materials like this, for example, if electron want to already make its transition from valence to conduction band, there is a hole over here. So if electron wants to jump back, it just needs to uh, change its energy by an energy, because it's have to change its energy because now it's at a high energy state. So energy have to conserve by emitting a photon, and energy will be conserved by emitting a photon. Such transitions are called the radiative transitions. So in the indirect band gap materials like silicon and germanium, because now we have to change its energy and also the momentum. So the phonon must be involved to conserve the momentum. So what are the phonons? Phonons are the quanta of vibrational waves, and phonons travel with the velocity of light, and their wavelength is determined by the crystal lattice constant, and phonons can only exist inside the crystals. So phonon will come to conserve, and the indirect band gap materials, phonon will come to conserve the momentum. uh, so these are the example of direct and indirect band gap materials. Okay, so now I'll discuss a little about the concept of effective mass. So if particle like behavior, mass is a fundamental property, but if we talk about wave like behavior, we must talk about the effective mass, not its fundamental mass. So if electrons have particle like property, its energy is directly p square divided by 2m, and m is the all its mass, fundamental mass. But if we discuss wave like behavior of electrons, we have to discuss its mass in terms of the effective mass. And also there is a term which is known as the mobility, which depend on the which depend inversely on the effective mass. It means that if the electron's effective mass will high or increase, its mobility will go down. So mobility is equal to q t c divided by effective mass, where t is the average time between the collisions. So in terms of the effective mass, if electrons is free, its energy is just is equal to p square divided by 2m. But because electron, if it's bound in a crystal, so it's not just to have its external energy, which we have provided as for example as voltage. Also we have it's have internal energy which is acting upon it. So which are the like electrostatic interaction from nucleus, or repulsive force from the neighboring electrons. So its energy is equal to is equal to p square divided by 2m n, which is the which m where m is the its effective mass, not is the mass actual mass here. So because the bound electron have external and internal energy, its mass is the now terms as the effective mass. So find the effective mass by ek diagram. If you want to find the effective mass by ek diagrams, so this is the energy term, which is half p square divided by 2m static, and then p is equal to h square k square divided by 2m static. And if we take the double derivative, we will get this term, and then by rearranging the equation, we will get m static is equal to h cut square divided by d square e divided by dk square. So this is the this shows the parabola ek. This double derivative shows the concave nature of this curve, because the single nature shows single derivative shows the slope, and the double derivative shows the concave nature of the curve. So if we want to find the effective mass of aluminium arsenide, for example, we have this energy and k diagram, and we have a we have a valence band, and we have their minima on the conduction band, and one minima here, like minimas we discuss here yeah, in this slide. This is the minima of the conduction band. uh, this is the minimum of the conduction band in 1 0 0 direction. This is the minimum of conduction band of 1 1 direction. So so these discuss the minima of in the conduction bands. So so if you want to know the effective mass at here, effective mass of the electron here, so now how we will do that? So because this is more concave than this, so this term will be this term will increase, because this is more concave. This is, so it have more d square concave, so it's more d square e divided by dk square value it will give. So which will decrease the effective mass. So here the electron here will have the less now lowest effective mass than these two electrons here. And also because the effective mass is inversely proportional to mobility, so the electron here will have higher mobility than these two electrons, probably higher mobility than these two electrons. So one thing which I didn't discuss here, that if of course electrons want to make a transition from 1 0 0 direction to 1 1 direction, which is has will be an anisotropy. For example, electron want to move from 1 0 0 to 1 1 1, probably here. So of course the now because the direction is changed in of course in the crystal the energy direction is changed, so here the band shape is also changed. So and it is very obvious from this diagram that if electron want to make its transitions from 1 0 0 to 1 1 1 direction, it's the band structure will be changed in this direction. So so this is how all about the direct and indirect band gap of semiconductors, and how we find the effective mass by EK diagrams, and how the effective mass of electrons in terms of mobility is important in EK diagrams. So because this in direct band gaps uh, uh, they emit a photon with a particular and mostly the direct band gaps materials are more efficient than indirect band gap materials, because they emit the photons in a visible range. So these direct band gap materials are used in LEDs and lasers. So the this is all for now. Thank you so much.